Hello everyone, welcome to GATE Academy Global. Okay, so in the previous session we talked about the injection of minority charge carriers, or we can say low level injection, and in that we have done one numerical problems, not completely because of the time limitation. I have given that one as assignment, and I have seen some of the students have answered that question in my comment box, and those students I can see Sarika is here and Manigandham, and one more students who has answered that one in my comment section in that video is I think his name is Saurav. Okay, so 3 students has answered that questions. I just want to see the name because he is not attending the classes, and he is watching the videos. Sanjay, okay, Sanjay Kumar Basu. So I have seen that the students has answered correctly because they knows the basic things behind this low level injection, that's why. And simply we have used the formula, and the question that I have asked you is on the basic formula that we have seen yesterday, and I wrote the formula there only, and you just have to put the values to get the answer. And I think the answer would be from the option that is B. And what is that question? That question is from this part, and we have seen that this is the question, this is the question. So what will be the answer? Okay, either A or B. A, I think, that is 1.5 into 10 to the power 13 per centimeter cube and 7.47 into 10 to the power 11. Okay, so I can see Sri Krishna is also answered today. Good morning sir. Answer is 1.5 into 10 to the power 13 per centimeter cube and 7.47 into 10 to the power 11 per centimeter cube. You just follow me, okay, you just follow me for answering, for commenting, for preparation of the interviews that you are going to face for your future examinations, and whatever the concepts that you want from this particular subjects. You are expecting that this I have this and this doubt, and I don't able to clear that doubt by reading the textbook or by watching any video. You just follow me, you are going to get the answer of that particular that you want from EDC subject. Okay, so I can see Sarika, Lakshmi, Amit, Hemant, Narendra, Advaid. Okay, Advaid, this is new person I can see. Okay, Abhishek Patel, Manigandham. Okay, good morning everyone. I think you all are following my lectures, and I am going to switch on to the next question in today's lecture. This is the crash course of EDC. Okay, so what is that question? Okay, we can see that a semiconductor is irradiated with light such that the carriers are uniformly generated throughout its volume. Okay, so uniformly generated means we have to answer this one with respect to time. Okay, because whenever the semiconductor is uniformly illuminated with light sources, the electrons or holes are generated within the semiconductor uniformly. In that case, there is no variation of the charge carriers with respect to distance, and because of that one we are going to analyze that semiconductor in which we have uniformly irradiated with light is analyzed in terms of its time. Okay, so we are going to see what are the other things that has been asked in this question. You just keep in your mind that we can analyze the illumination of light in 2 different parameters, one is with respect to time, with respect to distance. So there are 2 parameters on which the light irradiation on a semiconductor can be analyzed. Okay, so you just pick out the figures, you just pick out the points that is necessary for understanding the questions. Okay, don't by heart or cram the everything that you have seen in the lectures. Okay, so you just pick out or figure out the things that is necessary for the examination or interview points. Okay, and write those points in your notebook that is known as the we can say the short notes book, and from there you can revise whenever you are going to appear in the examination. Either it is mock test, or we can say either it is a main test, or we can say the examination, then you just refer those short notes to get the concepts very quickly, and you can get the answers while writing the examination very quickly, because every examination will have some time limitation, and if you answer properly by within that time limitation, it is only possible if you are having hand pickup of formulas and the steps that is followed by those formulas, then only you can answer the questions that has been asked in the examination within that hours that has been specified in the examination, either 3 hours, 1 hours and whatever. So, I can see the semiconductor is n-type and Nd is equal to 10 to the power 19 per centimeter cube. Okay, the semiconductor is n-type, that means the donor atom concentration is given. If the excess electrons concentration in the steady state is delta n, so it is an n-type semiconductor and excess electron concentration is given. So, I just write we are having an n-type semiconductor and this n-type semiconductor is uniformly, I will write here. Okay. So, we are having an n-type semiconductor and this n-type semiconductor is uniformly illuminated with light. So, it is uniformly illumination with light source. So, the next point is, definitely we know the answer, but analysis of the question is very important, because without analyzing the question that has been asked in the previous GATE examination, we are not going to get the proper answer of new questions. So, analysis of question is most important thing while we are figure out the important points from any of the questions. Okay. So, uniformly illuminated with light, when it is uniformly illuminated with light, then what will happen inside this semiconductor? Sir, generation will take place. So, we know that the generation takes place, and because of this generation what will happen? Sir, if the semiconductor is of n type, then we know that we are having Nd is nothing but n in n, and this is at equilibrium. This is the majority charge carrier concentration present in an n-type semiconductor. Now, after illumination we are having some excess concentration. So, how we can write this excess concentration? This is excess concentration. So, we have two things here. What are those two things? Sir, this is nothing but the initial concentration of majority, and this is nothing but the excess concentration after illumination. Excess concentration after illumination. So, these are the two things that has been present inside the semiconductor, which gives the total concentration of electrons within the semiconductor. But since it is an n-type semiconductor, the majority charge carrier concentration is initially it is very large in quantity. Okay, this is very large in quantity. So, if we have added some more amount of charge carriers by illuminating with light, then this will be very less in quantity. So, we just ignore the presence of this excess carrier concentration in presence of this majority charge carrier concentration. So, now we are going on to the next one, that is for the holes concentration, and the holes concentration in n type is nothing but the minority. Okay. So, we are going to be analyzed now the minority. So, what is this? This is nothing but the majority charge carrier concentration, which is the addition of initially thermal equilibrium majority charge carrier concentration and the excess concentration. It will give rise to the minorities also. So, initially we know what will be the minority. Sir, this is P n naught, this is the initial minority. So, this is the initial value of minority concentration that is present, plus the excess minority is given by delta P, or many times this delta P is also represented by, this is P dash n of T with respect to time if it is written. Okay. So, now this is delta P, and delta P is what? So, delta P is nothing but the excess concentration when we illuminate the semiconductor with light. This is nothing but the excess concentration. This is what? This is initial concentration. So, in that way you can make your own story. So, do not follow any other things. You can just think about the semiconductor, because this is very much required for EDC subject, that you can analyze the things properly in your own way. Do not always follow what is written in the question and what is written in the textbooks. You can make your own story by analyzing the things properly. If you match your story with the written story in the textbook, then definitely you are going to get the good concept. Okay, whenever we are having some doubt, you just ask me or correct yourself, or by reading the textbook you can also correct the doubts that you are facing. In delta n is equal to delta p, yes, here we are having delta n is equal to delta p, because whatever the charge carriers has been generated, the charge carriers will get generated when the electrons from the valence band will move to the conduction band, Advait. And when the electrons are moving, definitely we are having the generated charge carriers, that is delta n must be equal to delta p. So here also, if it is an n-type semiconductor, we just write, if the excess electron concentration in the steady state is delta n. So steady state means the final state where we are having, there is no change in the further thing. That means this stage will be come into existence whenever the semiconductor is placed for a long time in the similar state, then this state is known as steady state condition. Okay. So here the semiconductor is illuminated with light, and now what will happen, the charge carriers has been generated, and that charge carriers has given by delta n, but it is must be equal to delta p. So here the steady state values are given, and that is given by 10 to the power of 15 per centimeter cube. This is the value. Okay, now it is given that, and if Tp is equal to, that means what Tp? Tp is nothing but the lifetime of the charge carriers, and it is given that this is equal to 10 microsecond. Then we have to find out what? Minority carriers, the generation rate due to irradiation. Generation rate means we can find out here G optical or G light is equal to, due to light we have to find out the answer. Please unlock me in your doubt clearance telegram group. Okay, I will try. I don't know whether you are logged or unlocked. Okay, I will try after my class. Electrons and holes generated in a pair, electron hole pair. Yes. So we just take this one here, and I will write here GL is equal to, either we can write this is delta n divided by tau n, or we can write this is delta p divided by tau p. That will mean the same. And you just write one thing, delta n, that is tau n need not be equal to tau p. You just write one thing, tau n need not be equal to tau p. This is one mandatory thing. This is the first thing that you should write. And second thing is that delta p should be always is equal to delta p. So that means the generated charge carriers within the semiconductors are always equal, either it is electrons or holes, they are equal to each other, but it is not mandatory that tau n is equal to tau p. Sometimes it may be equal, sometimes it not be equal, but these values are found practically. Okay, what is tau n and tau p? These values are found practically. So we just need to find out here what is GL, and GL can be find out here because tau p is given, so I am using that one. And delta p and delta n are equal, so we can use this is equal to 10 to the power of 15 per centimeter cube divided by, what is the time that is given? Time is 10 microsecond, that means 10 into 10 to the power of minus 6 microsecond it is given, and here it is per centimeter cube. So the unit is per centimeter cube per second, and this is the unit of generation rate, and we just take this one into consideration, that is 10 to the power 15 plus 10 to the power 5, because 10 to the power minus 6 multiplied by 10, that is equal to 10 to the power 5 and minus 5, and if it is taken into numerator, this will become 10 to the power of 20 per centimeter cube per second, and this will be the correct answer. So where it is given is 10 to the power of 20 electrons hole pair per centimeter cube per second. So in this way we can analyze the questions by yourself, and you can answer the question by yourself, and you can make your own story behind each and every questions that you are facing, and at the end when you solve every question you can have the proper concept of whatever topics you are studying. Okay. So in this way we can answer. So this is one question that has been finished. So second question, What is this question? I am sorry. Under low level injection assumption, the injected minority carrier current for an intrinsic semiconductor is essentially. So, under low level injection, that means whenever the charge carriers are injected from one end of the semiconductor, okay. So, that is nothing but injection, okay. Whenever the charge carriers are injecting from one end of the semiconductor, this is nothing but the injection. I have given you the example of the syringe and with some skin. So, we are inserting the medicine that is present in the syringe in our body, and that is injected from where? Via skin. So, that is why we are also having the injection of minority charge carriers, means the minority charge carriers has been generated at one edge of the semiconductor and it has been injected into the semiconductor because of what? So, we can have the answer under low level injection assumption, the injected minority carrier current for an extrinsic semiconductor is essentially the. So, here we are having the direct answer. This is because of diffusion current, not drift current, not recombination current, not induced current. We are going to see the recombination current in the next chapters, that is in BJT. We are going to see what is actually recombination current. We know what is drift current. Drift current is the current which can be said to be the current due to the presence of electric field. But here we are not applying any electric field because the charge carriers has been generated due to illumination of light. So, we are not applying any electric field. So, we can write here that under low level injection, okay, just use another slide and I am using, and we just draw a we can say a visualization to understand the things properly. So, this is a semiconductor and we are going to apply a light source here. And when we are applying a light source, this is known as low level injection. Why it is called low level injection? So, everybody those who are watching this lecture know that why it is called low level injection. I think the low level injection means the injected minority charge carriers. Suppose this is an N type semiconductor and the injected minority charge carriers is Pn, and we just write this is P dash N and this is from 0. So, if it is 0 and suppose this is the length L, then P dash N of x is nothing but the excess minority charge carriers and it has been injected into the semiconductor. So, this is the excess minorities, okay. And the first thing that we can say that these minorities can be seen on this particular edge. So, initially when we place this semiconductor at 300 Kelvin, then we can write what are the majorities and minorities within these semiconductors. Majorities in this N type is nothing but ND or N in N at thermal equilibrium, N in at thermal equilibrium, N in at thermal equilibrium, like this. And we can write the minority, that is P in N at thermal equilibrium, P in N at thermal equilibrium, P in N at thermal equilibrium. So, what is the meaning of this thermal equilibrium? The presence of temperature is 300 Kelvin and we are not going to change the temperature value. That means the thermal equilibrium. So, these are the charge carriers which is present within the semiconductor, which is an N type semiconductor at thermal equilibrium. Now, what will happen? We are going to apply some light source. So, when the light is on, then we can have the generation at this particular edge. When it has been generated, we just write here this is delta N and this has been increased from delta P, okay. But we know that delta N must be equal to how much? Delta N must be equal to delta P. So, this is already known. Now, what will happen? There must be a change in concentration. So, concentration gradient. So, I just write here concentration gradient, is can be seen when we have low level injection. And if it is having a concentration gradient, definitely the diffusion of charge carriers is taking place and second is simultaneously the recombination of charge carriers is taken place. So initially we are having the injection. So injection, then we are having what? Diffusion, then we are having recombination. So these three are the three process that is taken place within the semiconductor when we are irradiating the semiconductor with some light source, and that is known as low level injection. So we have the meaning of each and every points that we have seen in our previous class. So I just write here that diffusion current is the correct answer. So drift current, why it is not having any drift current? Because if it is a low level injection, so low level injection means there is no electric field present, and if it is no electric field present externally to the semiconductor, then definitely the diffusion current is occurring inside the semiconductor. So we have answered this question, and now we are having another question, that is fourth question. And an n-type silicon sample is uniformly illuminated with light source which generates 10 to the power 20 electron holes pair per centimeter cube. Second, the minority carrier lifetime in the sample is 1 microsecond. So again we are having, we just write the things here, again we are having an n-type semiconductor. So we are having an n-type semiconductor. Silicon sample is uniformly illuminated. So here again we are having uniform illumination. So now we are catching the catching the illumination, catching the terminologies that is present. So initially I think when we answered previously this type of question, we never think about why it is written uniformly illuminated. Now we know that what is the meaning of uniformly illuminated. That means inside the volume the illumination of light are equal, and we can say that the generation of charge carriers within the semiconductor is not changing with respect to its volume or with respect to its distance. That is known as uniform illumination. So non-uniform illumination means the semiconductor is illuminated at only one edge of the semiconductor, like that we have seen in our previous class, question. Okay, illuminated with light which generates 10 to the power 20. That means here we can write electron hole pair, that is delta n is equal to delta p is equal to 10 to the power 20 electron hole pair per centimeter cube per second. So that means if it is per centimeter cube per second, if it is written in this way, so if second comes here, then definitely we can say that this is nothing but the generation rate. If it is a generation rate, then definitely we cannot write in this way. So there must be the other way of writing these things, that is nothing but the generation due to the light source, that is given by, either we can write this is given by delta p divided by tau p, or we can write delta n divided by tau n, or we can write in this way, this is p dash n of x, or here if it is illuminated uniformly n of t divided by tau p. So in this way we can write. So because the unit I have cared, this is given by 10 to the power 20. So the unit is electron hole pair per centimeter cube per second. So I just write here per centimeter cube per second. Okay. The minority carrier's lifetime in the sample is 1 microsecond. So the minority carriers means if it is an n-type semiconductor, what is the minority carriers present? That is nothing but the p, and we just come to know that here we are having tau p is equal to how much? This is 1 microsecond it is given. Okay. In the steady state means whatever is the condition, the semiconductor is placed in that condition for a long enough of time. That is, now it's come to in steady state condition. In the steady state, the Hose concentration in the sample is approximately 10 to the power of x. So at a steady state condition, the Hose concentration is given by 10 to the power x, where x is an integer, the value of x is. So we have to find out the Hose concentration inside this semiconductor. Now, if it is n-type semiconductor, the Hose concentration can be find out p dash n of t. This is nothing but the Hose concentration. So I just write here, we can find out p dash n of t at any time is given by GL that is the generation rate due to optical generation, which is given by G opt or GL, and if it is multiplied by tau p, then we can get the answer easily, okay, very easily, okay. So GL can be written as this is 10 to the power of 20, and tau p can be written as, okay, this is tau p which is given in the question, that is 1 into 10 to the power of minus 6. So that is given by 10 to the power 20 multiplied by 10 to the power minus 6, that is given by 10 to the power here 14, then we can write the x, value of x is equal to 14. So this is another important question, and Advaith is answering so properly and so quickly that I must appreciate his answer, okay. So sometimes because of hurry, okay, Advaith has answered differently the similar question. I have seen that his answer 26. So don't be in hurry, take a good analysis of the question, think about each and every points, each and every formulas that you have to we are going to use to solve the questions. So by proper concept and proper formula only you can solve the question that has been asked in IIT faculty's questions, IIT, that is the examination that is conducted by IIT Kanpur. So we just have observed so much of things that is being present at a particular point of time within our mind, because right now we are only studying this EDC, suppose, because this class is of EDC, then we have to think that when we are sitting in the examination hall, there are many much formulas that is running in our mind, because there the question is not only from EDC, they will conduct examination in mathematics, aptitude, EDC control systems, digital signal systems, communication, EMT. That means we are having the 10 different subjects, and the formula based on these 10 different subjects is to be present in our mind. So at that time you just take care that you just not answered incorrectly, because incorrect answer definitely take your marks, okay. So take care this part. So that's why I am taking time to give you the better understanding of the questions. So you can solve the question, I know, but by proper analyzing the question, if you answer, then only you can get the answer correctly. Yes sir. Okay, Milan Kumar Singh, thank you Milan, you just understanding what I am saying in terms of this examination point of view. An n-type silicon bar is illuminated at one end, x is equal to 0. The minority carrier concentration variation is shown in the figure below. Given Ni is equal to 1.5 into 10 to the power 10 per centimeter cube at 300 Kelvin, and D is equal to 13 centimeter per second. So there is a graph which is given in that question, and that graph is drawn in this way. So here we are having an n-type silicon bar is illuminated at one end, x is equal to 0. Now here the semiconductor is not illuminated uniformly throughout the volume. Now the semiconductor is illuminated at one end, So definitely we can see that low level injection condition prevails here, and if the low level injection condition prevails, definitely we can see the change in the concentration of minority charge carriers within the semiconductor with respect to distance, and that change can be written in exponential form. So now here this is the graph. In this graph we just take care that this is Pn of x, that means the minority, because the semiconductor is of n type again, and we are carrying that we have written here the minority carrier concentration Pn of x per centimeter cube. The bar is illuminated at one end, x is equal to 0. X is equal to 0 means it is illuminated at only one end. The minority carrier concentration variation is shown in the figure. This is the variation. So here we can see there is one line which is representing this value. Then definitely if it is visible, then I can write this is 1 into 10 to the power of 8, and that is nothing but the thermally generated minority carrier concentration, not optically generated minority carrier concentration. So this is the concentration of minority charge carriers that is present within the semiconductor, and it is not changing with respect to distance within the semiconductor. It is throughout constant within the semiconductor. Why? The reason is that the semiconductor is at 300 Kelvin. If it is placed at 300 Kelvin, then definitely we are having this concentration which is not changing with respect to distance. Now from here to here, this particular part, this is the initially present minority carrier concentration, and this is generated because of temperature which is given by 300 Kelvin. Now some of the more charge carriers has been generated. The reason of this charge carriers which has been generated, which can be find out by using delta P, it is given by, okay, at distance what? At distance 0. So this also can be written as P dash n of 0 is equal to, this can be find out by taking the difference between these two, because only this part is nothing but delta P, okay, from here to here. This is the initial concentration, this is the excess concentration. So we can find out this part by using taking 2 into 10 to the power of 8 minus 1 into 10 to the power of 8. This is given by how much? This is given by 1 into 10 to the power of 8. That means we know what will be the concentration at distance 0 within the semiconductor. Distance 0 means at the edge where we have illuminated the light source. So now I think we doesn't need any more plottings or diagrams, because now we can visualize the things. So I have trained you in such a way that you can visualize the things by your eyes whenever some questions has been asked in that particular part which we have visualized already. Okay. So now we know this part, this is the first part, and we know this is the second part. So we are having the initial concentration and excess concentration both. So this is the initial concentration 1 in 10 to the power of 8, and again the excess concentration is again similar, that is 1 in 10 to the power of 8. So Ni is given and D is given, everything is given. Now we can have to see what is the other things that has been asked in the question. The electrons concentration at thermal equilibrium is easy. So we have to find out what will be the electrons concentration at thermal equilibrium condition. So electrons, if it is electrons concentration, then we have to find out the majority. Okay, first time we are finding out the majority concentration at thermal equilibrium, thermal equilibrium means when the temperature is equal to 300 Kelvin and we are not going to change the temperature. So from this particular part, since in this question there is nothing given how much donor atoms has been doped, if it is given that how much donor atoms has been doped inside the semiconductor, then we can easily find out that for getting this one we can write Nd is equal to N in N type semiconductor is equal to the doping concentration, is equal to the doping concentration of the semiconductor, but it is not given in the question. It simply written that this is an N type of semiconductor. If it is not given, then how can we find out? We can find out these things by using mass action law. So what is that mass action law? I just write here, by using mass action law we can write mass action law. Why I am using mass action law? You just come to know that N in N type semiconductor at thermal equilibrium, P in N type semiconductor at thermal equilibrium. This mass action law is equal to Ni square when we are having working in thermal equilibrium condition. So this particular formula can only be applicable for thermal equilibrium condition. If it is not in thermal equilibrium condition, that means we are applying some other source of energy to the semiconductor, then we cannot write N in N naught into P in N naught need not be equal to Ni square for non-equilibrium condition, So we are going to see that part also, but if it is in thermal equilibrium condition, we can apply this theory. So here the question asked about thermal equilibrium condition, that's why we are applying this particular formula for understanding. So when the light source is applied, okay, when the light source is applied, the semiconductor is not in thermal equilibrium condition. Now the semiconductor is a non-equilibrium condition. If it is in non-equilibrium condition, then we cannot apply Pn naught N in N naught into P in N naught is equal to Ni square. So, the question that is asked here is nothing but thermal equilibrium. Thermal equilibrium means we can apply this formula. So, if we are applying this formula, then we can write this is N in N naught is equal to this is Ni square divided by P N naught. So, what is Ni square? From this particular questions we can take Ni square. See here, this is 1.5 into 10 to the power of 10. This is the value of Ni. So, here we are taking 1.5 into 10 to the power 10, that is equal to 2.25 into 10 to the power of 10 into 10, that is 20, divided by Pn naught. How much it is? Pn naught. So, this is given by this value, because this is the host concentration in N-type semiconductor at thermal equilibrium. So, this is given by Pn naught, which is 1 into 10 to the power of 8, 1 into 10 to the power of 8. That is given by, this is 2.25 into 10 to the power of, this is 12 per centimeter cube. This is the concentration of donor atoms within the semiconductor at thermal equilibrium. Why it is called concentration of donor atoms? Because this is also given by Nd. So, very simple. So, I can see that Sri Krishna has answered, Narendra Reddy has answered, Advaid is answered, and sir test series score low aa raha hai. Why you are getting low scores? The reason that you are not analyzed the previous year paper properly, you have not a hand pick up of formulas, we have not following the steps, and your level of preparation is not up to the mark. So, initially when we are preparing for the examination, initially you are feeling that you are going like a linear. That means while preparation, so every student is facing this problem. I just give you some analysis. So, while preparation, whenever we are preparing, so this is the graph which is representing the, so what is the level of preparation, and I just write here, this is y axis, and for students like Gaikwad Chetan, you just understand, and this is the time. Time means either it is, we can take month or year. Okay. So, like this you are preparing. So, initially when we are preparing, either you are taking self study or you are preparing by any other sources like YouTube videos or taking the coaching centers training, then initially if you are under the training, then definitely you are, as the time goes in your institutes or in YouTubes, like you are preparing for my video, then you are thinking that you are preparing in this way. As the time goes, your preparation level is also increasing, and you are in full confident that every concepts I am studying, I am getting that concept, and you are in more confidence, because as the time goes, this is a linear graph, your preparation level and your time will be increasing simultaneously. Then after some time, your faculty left you, and at this time you are not able to prepare, because the linear graph now you are not going to get, because the faculty has finished this subject and you stop studying the subject, then your preparation is not going in that way as we have seen earlier. Now, what will happen? This is the time we have to do more analysis on what? More analysis on questions and more analysis. This is the time. This is the query time. And this is the time we have to do more questions from any other source, either from the textbooks, or you should have the proper revision, because your faculty has left you. Because now he is going to be, you are going to prepare by yourself. Now, what will happen if you are not doing this one? Then your either your preparation level will decrease, or either you are making a plateau, a similar level, the saturation condition. Whatever you have prepared, you are in the similar condition. So, in that condition, you are trying for a test. In that condition, you are trying for a test. Then what will happen if you are trying for appearing in a test series, and if you have not done this much analysis by yourself, then definitely you are not able to get a good score. So if you are continuously want this level linearly will increase, then definitely you must have do this particular thing, questions, new questions and revisions. So if you are doing that only, you can prepare well. Otherwise you are in a plateau, or your preparation level will decrease like this. And if it goes for a month, from I can say it will goes up to December. So if you are continuously appearing for test series, then you are going to get more questions, and if you are continuously appearing in test series, you are going to get more revisions. And if you are doing these two things by appearing in the test series, you are thinking that you are in a plateau, or your level of marks will not increase. But continuously if you are doing hard work, then what will happen? Finally you are going to get, from the month of December, your plateau is increasing suddenly, and your preparation level will increase like this. Okay. So just understand these things. So every student are facing these things. So test means you are in a plateau and you are continuously get the problems and revisions. Thank you Advaith Vankar, and I am very thankful to you. You have compared me from Kalmakar's sir. Okay. So I very few concepts I have seen from his video, but that's why I am not able to read his name also. From I think I have seen his video in 2012. So I just want to analyze this one. I have answered the question that has been asked from this student, that is Gaikwad Chetan. Okay. Now an N-type semiconductor we have, and we just take the another questions that has been asked. The second part, the diffusion length of holes is. The diffusion length of holes is. So we have to find out the diffusion length. So what is the diffusion length? Sir, diffusion length of holes means here they are asking about LP. So LP can be find out by how many ways? So LP, LDTD, or we can write this is L is equal to root over dP into tau p. This formula already we have seen in our previous class. Now the diffusion length of holes can be find out by some other way also. How? What is the way by which we can find out for low level injection? Sir, we can find out this part by using another analysis. What is that analysis, sir? The excess carrier concentration in an N-type semiconductor can also be written as the excess carrier concentration at distance 0 into e raised to minus x upon LP. This is another formula by which we can get. So why we are writing this formula? The reason is that we have something in our graphical plot. What is that graphical plot? Suddenly this graph come. Okay, so what is that graphical plot? Sir, graphical plots have some particular values by which we can find out. Here we can see this is the distance. What is the distance? Distance is equal to 0.02 mm. So we should write that at distance 0.02 mm we have this value. What is this value? This is given by 1 upon E into 10 to the power of 8, and this particular small dark arrow shows that this is nothing but the concentration of generated charge carriers or excess charge carriers at this particular distance, and we can write this is nothing but P dash in N-type semiconductor at distance 0.02, okay, at distance 0.02. So at this particular distance we are having excess charge carrier concentration, and the value of that excess carrier concentration in a N-type semiconductor is given. Now what we have to do? We have to simply write the equation, that is P dash n at 0.02 is given by this is P dash n of 0 into e raised to. This is again minus x, where x is equal to minus 0.02 divided by LP. You just take care that this particular value is written in the form of millimeter. So here we are writing this is in millimeter. So only one thing that is unknown here, And what is that thing? That is nothing but LP. Do you know the value of P dash n of 0? Yes, we know the value of P dash n of 0 is nothing but what will be the excess concentration at distance 0, and that is given by the difference of these two, that is 2 into 10 to the power of 8 minus 1 into 10 to the power of 8 will give the value of P dash n of 0. Everything is given in the graph. So, we just write this will be equal to 1 into 10 to the power of 8 into e raised to, what is next? This is minus of 0.02 mm divided by, we just write here LP, and what is P dash n of 0.02? That is given by 1 upon E into 10 to the power of 8. Use this formula. There is only one thing that is unknown in this formula, that is given by LP. So, we can find out the value of LP from here. So, what is LP? LP is the diffusion length. At the diffusion length, you just remember one concept here. I will give you that concept. Okay. So, what is that concept? The concept is that at diffusion length in low level injection, the concentration of excess minority carriers in the semiconductor is, it is given by, so we just have this question. So, we have to answer this question. How to answer? We can find out at diffusion length what will be the concentration of excess minority carrier concentration. So, the diffusion length is given by suppose LP. So, we just have to find out what is P dash n of at distance LP. This is given by, this is P dash n of 0 into e raised to minus x divided by LP, that is given by minus of LP divided by LP, that is given by 1 upon E into P dash n of 0. That is at diffusion length the concentration is decreased by 1 upon E times the concentration at distance is equal to 0. That means, this will be the concentration of excess minority charge carrier concentration at distance LP. So, here if I write this one 1 upon E into 10 to the power of 8, then we can figure out this thing 1 upon E into 10 to the power 8. What is this? This is nothing but the concentration of excess minority charge carriers concentration at diffusion length. That means 0.02 is nothing but the diffusion length LP, 0.02 mm. So, whenever we understood this concept, we just need not to find out this, write this particular equation to find out the equation. So, what we have to write out? So, we just have to understand that 1 upon E into 10 to the power 8 is nothing but the concentration of the charge carriers at diffusion length. That means, for this particular question, we can write the LP distance. If you find out from this formula also, we can get the LP distance, but if not, if you know the concept properly, what I have written here, then definitely you can say for this particular question LP is equal to 0.02 mm without writing any formula, if you know this particular concept. So, the concentration of excess minority charge carrier concentration at distance, that is nothing but the diffusion length, will be decreased by 1 upon E times the initial concentration at distance 0. Okay. So, if it is okay, then you just see here that we can write here this is 0. Those who have found out the answer, they also knows this concept. So, we can write here this is equal to 0.02 and mm is written already in this question. Okay. What happened, Deepak Barnwal? The lifetime of hole is, now we have to find out the lifetime. Okay. So, what will be the lifetime? So, we know that LP is equal to root over dP into tau p. Okay. So now we are having the lifetime, that means if, that is given by tau p is equal to, this is given by LP square divided by dP. Why I have written this formula? The reason is that we know the value of LP square. What is the value of LP square? LP square is nothing but this is 0.02 into 10 to the power of minus 3 and the square of this one, because it is given in mm, and dP is already given in the question. dP is already given in the question, that is why I have written this formula. So what is this dP? So we can see the dP value. So dP value, dP is given 13 centimeter square per second. So we just take this one and find out the solution. So take this concept into your account. At diffusion length, the concentration of minority charge carriers will be decreased by 1 upon E times the concentration of excess charge carrier concentration at distance 0. You just remember and figure out the things that is very much required for understanding the concept. And now we have answered, that is what is tau p. Tau p is equal to LP square divided by dP. So here LP square is nothing but this is 0.02 mm and the square of this one, and dP is given by how much? This is 13 centimeter square per second. So we just take this one, 13 centimeter square per second. So here it is having the unit centimeter square, here it is having unit millimeter, that means one of the unit has to be converted. You just convert the numerator, that is equal to 0.02 into 10 to the power of minus 3, and this is again 10 to the power minus 3, that will be given by 10 to the power of minus 6. Okay, now it has been converted into centimeter again. So meter is converted into centimeter. So we have to write the meter, if it is converted into centimeter, millimeter, it is millimeter. So now the unit will be in a meter square. The unit will be in meter square. Now it has to be converted into centimeter. When meter is converted into centimeter, so it has to be increased. So we have to write this will be multiplied 10 to the power of, this is square and square, that is 4. So we just write here in this way. So if you know the properly the conversion, then you can do it by your own. So if it is multiplied by 10 to the power 4, then we are getting, that is 0.02 into 10 to the power of minus 2. So in that condition we can find out the answer. So this will be given by how much I am getting, this is 0.307, and I think the unit is already given in the question. What is the unit? Microsecond. So I just take this one and this is microsecond. PN junction class will start from 5th. Today is 3rd. From 5th onwards we are starting PN junction. So this question is over. Now we are having another questions, that is as shown in the shown a uniformly doped silicons bar of length L is equal to 0.1 micrometer with a donor concentration Nd is equal to 10 to the power 16. That means a light source is applied, donor concentration 10 to the power 16. It has been applied at x is equal to 0 and the overall length L is equal to 0.1 micrometer, such that the electrons holes pairs are generated. So now we are having the generation rate GL. So here the generation rate GL is written in this way. So what is the meaning of this one? We are going to find out. What is GL naught? GL naught is equal to 10 to the power 17 per centimeter cube. Whole lifetime is 10 to the power of minus 4 second. Electrons, charge, hole diffusion, everything is given. Low level injection condition prevails. Assuming that the linearly decaying steady state excess holes concentration that goes to 0 at x is equal to L. Okay. The magnitude of the diffusion current density at x is equal to L by 2 in ampere per centimeter square. So we have to find out the diffusion current density. So we just write here that in this question, which number? Question number 8. So we have to find out, first thing is that we have to find out the diffusion current density and density, diffusion current density. So now what is the type of semiconductor? The type of semiconductor is N type. So which charge carriers is diffusing inside this semiconductor? So the charge carriers which is diffusing inside the semiconductor is nothing but the holes. So holes are diffusing inside the semiconductor. That means we have to find out the diffusion current density due to holes at which distance, which is changing with respect to distance. X is equal to L by 2. So this is the distance at which we have to find out. So what will be the formula? The formula is equal to minus q into dp, and this is dp dash n of x divided by dx, because the excess carrier concentration is diffusing within the semiconductor. So initially what will be the charge carriers? That is constant, it is not diffusing. The excess carrier concentration is diffusing, that's why I have written here p dash n of x. So here it has also been written that the charge carriers are diffusing linearly, assuming a linearly decaying steady state excess hole concentration that goes to 0 at x is equal to L. So we are having a linearly decaying, the charge carriers are linearly decaying, and it will goes to 0 at x is equal to L. So the same thing can be drawn here, and we just draw the similar thing. So suppose this is the semiconductor, and this is the distance x is equal to 0, and this is the distance x is equal to L. And we can draw the graph. What is the graph representing? The graph representing how the charge carriers is changing with respect to distance. So we can have this distance is x in centimeter, and this is the minority carrier concentration P in N, which is changing with respect to 0. And we just know that initially we have the carrier concentration, there is nothing given with respect to temperature. So we can draw a graph which is drawn by using a similar line which shows the dimension, and it will goes to 0. So we can write that this is nothing but the concentration, that is P dash N, which is changing with respect to x, and it goes to 0 at distance x is equal to L. So we have some point that is x is equal to L by 2 somewhere here, and this is 0 point. So this is the concentration of excess minority charge carriers within this N type semiconductor, which is going to be 0 at distance x is equal to, here we are having x is equal to L. So this is the things that is given in the question. Okay, now what will I have to write here? So we have to find out this formula. So in this formula what is given? Nothing is given, only q and dp is given. So we just have to think about how to find out p dash n of x divided by dx. So do you know what is p dash d of, what is p dash n of x? This is nothing but the excess carrier concentration, and this excess carrier concentration can be find out. This is nothing but a question mark. So this excess carrier concentration can be find out by using the generation rate. So optical generation can be given by J of L, and this is given by p dash n of x divided by tau. Okay, we know this formula, that tau p. So this is the excess carrier concentration, and this is tau p, and this p dash n of x can be written as p dash n of 0 into e raised to minus x divided by Lp, and this is given by tau p. One more thing. So what is this p dash n of 0 divided by tau p? This is nothing but this, since we know that p dash n of 0 divided by tau p can also be written as GL. Here it is changing with respect to distance, and if it is at 0 distance, we can write this is GL at 0 distance. So which is also can be written as GL naught. That means the concentration which has been generated with respect to time at distance 0, which is also be written as GL naught. Now we can write this GL of x in another way, that is given by GL naught into e raised to minus x divided by Lp. This is the another way of writing this GL of x. If we have taken that p dash n of 0 divided by tau p is equal to GL naught, this is nothing but the generation rate at distance 0. This is nothing but the generation rate of charge carriers at distance 0 due to illumination of light. So now if this particular thing, that is e raised to minus x upon LP, this is nothing but the exponential function. This is what? This is nothing but the exponential function which is changing with respect to distance. If I will take, so now what I am taking, if x is very less, then the exponential function which has been in this way, if the distance is very less, so x, this is 0, this is x which is very less, then we can say this particular line is said to be linear, this line is said to be linear. So if x is very less, then this exponential function can be written in the linear form. And if we expand by using the linearity, then we are going to get this GL of x is equal to GL naught 1 minus x divided by LP if the higher order terms of x will get neglected. So the similar thing is given in this question. GL is equal to GL naught 1 minus x divided by L. So we can see that one. And here we are having what is the generation rate at distance 0, it is given 10 to the power 17. So we can write here the similar thing is given in the question which we have analyzed properly, and we are having GL of x is equal to 10 to the power of 17 into 1 minus x divided by L at any particular distance it is measured. So this is given in the question 10 to the power 17 1 minus x divided by L. So now what is my question? My question, in this question we have to find out this particular part, and for getting this particular part we have to find out what is p dash n of x, because if you know what is p dash n of x, this part, then we are going to derive this one for getting the value of the diffusion current density at distance x is equal to L by 2. So this p dash n of x can be find out by using this formula, that is given by p dash n of x is equal to, this is given by GL of x multiplied by tau p, and GL of x is already given, this is given by GL naught. So I must take here another particular, because so we are going to find out p dash n of x, this is given by GL at any distance of x into tau p, and we know what is GL at any distance, this is GL naught 1 minus x divided by L into tau p, and this will be given by 10 to the power 17 into 1 minus x divided by L, okay, and this is nothing but p dash n of x. So here it is x, here it is x, and what is tau p? Tau p is already given in the question. Where is that tau p? So we just find out the value of tau p. Whole lifetime is equal to 10 to the power of minus 4 second. So this is given by 10 to the power of minus 4. So this is in second, and the generation rate is already given in centimeter cube per second. So this second and second will get cancelled, and we are going to get what is p dash n of x, which is nothing but the concentration. This is given by 10 to the power 13 1 minus x divided by L. So this is the overall formula p dash n of x. Now we don't require this formula because we need what is dp dash n of x divided by dx. We just need this one. So how to get this one? This is 10 to the power 13, which is constant, and this is 1. The derivative of 1 with respect to x will become 0, and this will become x divided by L. That means we are getting 1 upon L. That means we are writing this is 10 to the power 13 with minus sign divided by L. It is given by, this is given by dp dash n of x divided by dx, and we know what is L. L is nothing but the length of the semiconductor which has been placed as a sample to do these following things. So we know what is dp dash n of x divided by dx, then we can find out what is jp of x, that is the diffusion current density at x is equal to L by 2. So here this particular formula is not depending on x, it is not depending on x. That's why we can say that the current density is also not depending on x. So here we can write this is minus q into dp, and this is minus 10 to the power of 13 divided by the distance L. Okay, this is the constant distance, and we are getting the overall value which will be positive. So this will be given by 1.6 into 10 to the power of minus 13 into dp, 1.6 into 10 to the power of minus 19, that is the charge of an electron. And what is the value of dp? dp is equal to 100 centimeter square. We just write here this is 100 centimeter square, and this is 10 to the power of 13 divided by the length of the semiconductor sample, which is given by 0.1 into 10 to the power of minus 4, that is in centimeter, because everything is given in centimeter. So very easy analysis. We have taken so much concepts from this question, and I think the answer would become, how much will be the answer? So those who have solved this question can tell me, 16 ampere per centimeter square, and the answer would become equal to 16 ampere per centimeter square. So those who are not getting this question can see this video again one more time, so that you can get a clear cut concept. Now it is the time to say goodbye. So have a happy concepts today, and you just analyze the things properly. And I thanks Advaid, Deepak, I don't know what he has written here. So Advaid, he has admired me so much in a good way. So that's why I want to say thank you to all of you. Those who are watching this video, I am now signing up, and if you are having a good concept over all these things, then definitely you may expect one questions in the upcoming GATE examination from this low level injection. That's why I have given so many things in this low level injection. Okay. So this is another very good questions that we have found in the previous year GATE examination, and now I say goodbye to all of you.